Hi everyone. In the last class, we have discussed about some important properties of invertible elements of a Banach algebra. In particular, we have shown that the set of all invertible elements is an open subset of A, and the map A going to A inverse is continuous on G of A, the set of all invertible elements of A. So today we are going to discuss few more important properties based on the earlier discussions. So in particular, we are going to discuss about the spectrum of an element in a Banach algebra. So we have shown that we have already discussed that if A is a unital complex Banach algebra, so we define G of A as set of all A in A such that A is invertible in A. Okay. So let us look at a few examples to understand how invertible elements look like in a Banach algebra. Let us take A to be set of all n by n matrices, and if you take A as Aij in A, then we know that A is invertible if and only if determinant of A is non-zero. So in this case, we can actually say that G of A is nothing but set of all A in Mn of C such that determinant of A is non-zero. The second example, let us take A to be C of K, where K is compact and Hausdorff of space. Now we know that if I take f in A, that means continuous function on K taking values in C, then f is invertible if and only if there exists G in A such that f of t into G of t is 1, that is G of t into f of t for every t in K. And in this case, whenever we can conclude that so inverse of f is nothing but 1 by f of t for all t in K, so that is G of t. So whenever f is invertible, we can say that f is invertible if and only if f of t is non-zero for every t in K. Now from that we can write down what is f inverse of t. In fact, this is nothing but 1 by f of t. Okay, this is one more example. Now the invertibility also depends on the algebra that we are looking at, so we will be discussing that point at a later stage. Now based on this invertibility, we can discuss about the spectrum of an element. So let us take A to be unital Banach algebra, and A is an element of A. Then we define the spectrum of A, which is denoted with this symbol, spectrum of A, with respect to the algebra A. Is set of all lambda in C such that A minus lambda into 1 is not in G of A. This is called the spectrum of A in the algebra A. That means the spectrum depends on the algebra that we are discussing with respect to the underlying algebra. And the complement of this is resolvent of A is set of all lambda in C such that A minus lambda 1 is in G of A. So this is called the resolvent set of A. And spectrum of A with respect to A is nothing but C minus the resolvent set. Now we can ask the question, what can we say about this spectrum? So why this is important? So we can show that the spectrum is non-empty. First of all, why this is important? Let us see one simple example to understand. That is, this is exactly in the case of n by n matrices. Let us take A to be set of all M and C, n in n. Now let us look at spectrum of some element A with respect to the algebra. This is set of all lambda in C such that A minus lambda I is not invertible in A set of all n by n matrices. Now this is nothing but, since A is a map from Cn to Cn, it is not invertible, means it is not 1 1, and that is equivalent to saying that it's not onto. So we can say that A minus lambda I is not 1 to 1. That means set of all lambda in C such that the null space of A minus lambda I is non-zero. So that means this is set of all lambda in such that there exists x non-zero, x in C power n, such that Ax equal to lambda x. From this we can say that this set is nothing but set of all eigenvalues of set of all lambda in C. Lambda is an eigenvalue of A. That means the spectrum concept is exact generalization of set of all eigenvalues of a matrix. Okay. Now let us try to look at spectrum of an element in a different Banach algebra. Let us take A to be C of K, where K is compact Hausdorff space. We have already discussed about the invertible element. If you take F in A, then spectrum of F with respect to this algebra A, this is nothing but set of all lambda in C such that F minus lambda into the constant function 1 is invertible, is not invertible. We know that a function is invertible if and only if it does not vanish at any point. So if it is invertible, it's not invertible means it vanishes at some point. So this is set of all lambda in C such that there exists some T naught in K such that f of T naught minus lambda into the constant function 1 acting on T naught, that is 1, this is 0. So this is nothing but set of all lambda in C such that f of t naught is lambda. Here this is 1, the constant. Okay, that means lambda is in the range of f. So this is exactly the range of f. Now if you look at the earlier case, the set of all eigenvalues is a finite set, and in the second case the set of all eigenvalues may be an infinite set, but its range of f, because f is defined on a compact set and f is continuous, the range is always compact. So this is a compact set. And earlier case also, this is also compact set. It contains only finitely many points. Okay. Now we can also ask the question, because we are writing subscript a, this invertibility depends on the algebra. So let us look at one more example. So let us take D to be set of all z in C with mod z less than 1. Define A of D, set of all functions from D to C, such that f is analytic in D and continuous on the boundary of D. You can show that this is subset of C of boundary of D. So we can, with respect pointwise addition, so if we take fg in AD, f plus g at t defined as ft plus gt for all t in D, alpha f ft alpha f of t for every alpha in C and t in D. So this is a vector space. Now look at supremum norm. So fg at t you take as f of t into g of t for every t in D, and norm of f is the supremum norm mod f of t, where t is coming from D closure. T is coming from D, so the maximum is attained on the boundary. So we can, with respect to these operations, it is a subalgebra of C of boundary of D, and in fact to show that it is closed subalgebra of C of D, C of boundary of D, so use Morera's theorem. To conclude AD is closed in C of boundary of D. So we can conclude that it's a Banach algebra, and let us take f of t equal to t for every t in D closure. Now spectrum of f with respect to C of boundary of D is nothing but boundary of D, whereas spectrum of f with respect to AD is nothing but closure of D. So we can say that the spectrums are different with respect to different algebras, but in our case we will be dealing all the time with one Banach algebra, so we will not write this subscript. So we always say that when A is a unital Banach algebra, with unit 1. If A is in A, spectrum of A we write as set of all lambda in C, so that A minus lambda 1 is not invertible in A. Okay. Now we want to ask the question, can we say that spectrum is non-empty? If we see both two examples, the first one is a non-commutative Banach algebra when n is bigger than or equal to 2, and the second one is commutative Banach algebra with union. In both cases, we have got that spectrum is always non-empty. In fact, we can conclude this as a result that the spectrum is always non-empty. If A is a unital Banach algebra, and A in A, then we can say that the spectrum is always non-empty. Okay, so let us look at the proof of this result. Let us look at case 1. A is not invertible. Then in this case, 0 is always in the spectrum of A, and spectrum is non-empty. So let us look at case 2. A is an invertible element. So let us assume that spectrum is empty. Then in this case, the resolvent set rho of A is the full complex plane. Okay, so let us take a functional phi from A star, where A star is nothing but the dual space of A. Define f from C into C by f of lambda as phi of A minus lambda 1 whole inverse. If lambda is in C, so lambda is in the resolvent, so A minus lambda inverse is meaningful. That's an element of the Banach algebra A, and when you compose with phi, this is an element of C. So we want to show that this f that we have defined is entire and bounded. If we show that it is entire and bounded, we can use the Livolli's theorem to conclude that it is a constant, and we show that that constant is 0. So from that we can conclude. So once the constant is 0, we show that f is 0, and this is true for every phi. That means phi of A minus lambda 1 inverse is 0 for every phi. That means A minus lambda in lambda 1 is 0, which is a contradiction. That is the idea of the proof. So let us try to look at to show that it is analytic. So the first step, f is entire. So let us take lambda naught in C. Let us see whether it is differentiable at lambda naught. So f lambda minus f lambda naught by lambda minus lambda naught. This is by definition. So let us look at, call this as equation 1. So this, since phi is a linear map, so this is phi of A minus lambda 1 inverse minus A minus lambda naught inverse divided by lambda minus lambda naught. So this we can write. Now we have already used this formula. So recall, B inverse minus A inverse is A minus B multiplied by B inverse A inverse. Now if you use this formula, so we will get phi of So the b you can take as a minus lambda 1, and b you replace b by a minus lambda naught. So you can say that a minus lambda 1 inverse, so a minus lambda 1 minus a plus lambda 1 multiplied by a minus lambda 1 whole inverse divided by lambda minus lambda. So this is nothing but okay. So we can actually cut down these things. You will get phi of a minus lambda 1 inverse multiplied by lambda minus lambda naught a minus lambda into 1 whole inverse divided by lambda minus lambda naught. So this is nothing but phi of a minus lambda 1 inverse multiplied by a minus lambda naught inverse. We will get this. Now we know that the map A going to A inverse is continuous. So whenever lambda goes to lambda naught, A minus lambda inverse goes to A minus lambda naught inverse. So this implies limit lambda tends to lambda naught, f lambda minus f lambda naught divided by lambda minus lambda naught is nothing but phi of a minus lambda naught multiplied by 1 inverse. So you will get power minus 2. So this means f lambda naught, f dash lambda naught exists. We have taken lambda naught to be arbitrary. So from this we can say that f is entire. So therefore f is entire. Now we want to say that f is bounded. Step 2. Okay. So let us look at if mod lambda is bigger than norm A, then we know that A minus lambda is invertible. So then we can say that by earlier calculations we can say that mod f lambda by definition, so this is norm phi multiplied by this is phi of a minus lambda 1 inverse, so this is norm of a minus lambda 1 whole inverse. So whenever mod lambda is bigger than norm A, you know that that is given by 1 by mod lambda minus norm A, and in fact this goes to 0 as mod lambda goes to infinity because norm phi is fixed. Okay, so outside the disk, if you look at disk with radius mod lambda, so outside this disk the function is bounded and in fact it goes to 0 as mod lambda goes to infinity, but the disk is compact, the closed disk is. So if you look at, so let us take B as set of all lambda in C that mod lambda less than or equal to norm A, so this is compact. So f is continuous on C implies that f of B is also bounded. So we have shown that f is bounded on B and f is also bounded on the complement of B. So we can say that therefore f is bounded. Now by the Liverlees theorem, f is constant. F is constant. But we know that f lambda goes to 0 as mod lambda going to infinity. As f lambda is going to 0 as these things. So we can conclude that f of lambda is 0 for every lambda in C. So that means we can say that phi of A minus lambda 1 whole inverse is 0 for every phi in A star. So phi of an element is 0 for every phi in A star by an application of Banach theorem. A minus lambda into y whole inverse is 0 by Banach theorem. So this is a contradiction. Because A minus lambda 1 whole inverse cannot be 0. If this is 0, so if you multiply with A minus lambda into 1 from the left hand side, you will get left hand side equal to 1 and right hand side it is 0, which is a contradiction. That means our assumption that spectrum of A is empty is wrong. So therefore we can say that spectrum of A cannot be empty. It is a non-empty subset of C. So this gives the proof of the result that in any unital Banach algebra, the spectrum of an element is non-empty. So using this, we can actually show that the Gelfand-Major theorem if A is a complex division Banach algebra, unital Banach algebra, then A is isomorphic with C. Here division algebra means every non-zero element is invertible. So let us look at the proof. Define eta from C into A by lambda is mapped to lambda times 1. 1 is the unit element of A. So then we can easily show that eta is linear 1 to 1. So eta is linear and norm of eta lambda in the algebra A. This is norm of lambda into 1. This is mod lambda into norm 1. We know that norm 1 is 1. So this mod lambda. So therefore eta is an isometry. We want to show that eta is onto. So let us take an element A in A. Then we know that spectrum of A is non-empty. So let us take mu from spectrum of A, then A minus mu into 1 is not invertible. So that means since A is a division algebra, hence we can say that A equal to mu into 1. Now we want to define, so eta, so therefore eta of mu is exactly mu into 1, that is A. So that is eta is onto. So we have shown that eta is isometry, linear and onto. So this gives isometric isomorphism from C into A. Okay, see, this is one of the well-known results known as Gelfand-Major theorem. And sometimes this the first result that we proved, this is also known as the Gelfand-Major theorem. Now let us look at some consequences of these results. So we have shown that spectrum is non-empty. So first we want to show that spectrum of A is bounded. So let us take, if mod lambda is strictly bigger than norm A, then we know that A minus lambda into 1 is invertible. We have already proved this result. So that means A minus lambda 1 is not invertible, implies mod lambda less than or equal to A. That means we can say that lambda is in the spectrum of A, implies that mod lambda is less than or equal to A. So therefore we can say that spectrum of A is contained set of all lambda in C such that mod lambda less than or equal to norm A. So we can conclude that spectrum is a bounded subset of C. So spectrum is some set like this, then this is norm A. So spectrum is bounded. Next we want to show that spectrum is a closed subset of C. Spectrum is closed. Okay. To show this, define a map F from rho of A into A lambda going to A minus lambda into 1. So we can show that this map is continuous. F is continuous. In fact, we can show that the claim is rho of A is exactly F inverse of GA. Okay. So lambda is in rho of A if and only if A minus lambda 1 is in G of A. So this is if and only if F lambda is in G of A. So this implies lambda is in F inverse of G of A. So since F is continuous and G of A is open, so this set is open. So inverse image of open set is open because F is continuous. So we can say that this is rho of A is, so the conclusion is that rho of A is open in C. But we know that spectrum is hence we can say that since spectrum of A is nothing but C minus rho of A, it must be closed. So we have shown that spectrum is a closed and bounded subset of C. It's also non-empty. So the conclusion from all these results is that spectrum of A is a non-empty compact subset of C. So far we have discussed about the spectrum is non-empty compact subset of C, and the Gelfand-Major theorem, which says that if A is a unital complex division Banach algebra, then that is isometrically isomorphic with C. So we will stop here. Thank you very much.